The next natural thing for us to study is gravitational potential difference. So we have moved on from, let's just have a recap. So gravitational force. So with this, we can talk about field. And with this, we can talk about potential difference, gravitational potential difference. Gravitational potential difference, potential energy, and what else? So gravitational potential, something called as gravitational potential also. I think post this we can do gravitational potential. Anyways, all these three can be understood with this sequence. Now let's recap the idea of potential difference. So it's quite simple. So potential difference, the idea of potential energy is to do with energy stored because of its configuration or if not position. Now the idea of potential difference is this actually, it's quite simple. See, if I keep an object, say at first instant, I'll keep it at, just a second, I'm trying to change the color. At first instance, I'll keep it at point B, and second instant, I'll keep it at point B, and the first instant, I'll keep it at point A. Now my question to you guys is, do they have the same potential energy? The potential energy at A, is it same as potential energy at B? No, right? So energy at A is clearly less than B. So when we talk about the word less, more, what are we doing? We are comparing. So things that we can compare, we can always subtract as well. Find the difference as well. For example, say this has around 23 joules of energy and this has around 16 joules of energy. And now the difference is 7, right? The difference is 7. So difference between the energy at point B and at point A is 7. So the difference over here is, difference in energy is, difference in energy is 4 plus 3 is 7. So that is your basic idea of potential difference, right guys? So same thing we'll be doing here as well. So we are considering a source which is of mass m. We'll consider 2 points, say A and B. And from the center to this center, from this center to this center, we have Ri and Rf. So this is our point A and this is our point B. To figure out the potential difference, we do external work. So we actually do the work and we move an object from point A to point B. And that object's mass has to be 1 unit actually. That's the definition of potential difference, that needs it to be 1 unit. But anyways, so we'll just make use of some object whose mass is m. So we are moving an object whose mass is m from point A to point B and trying to figure out the work, and post that we will figure out the potential difference between A and B. Again, it's a very simple concept. Potential difference is the difference in energy between the two given points. Okay. See, we will use a word called as quasi-static movement, and we're talking about its condition as well. Quasi-static means, it literally means very, very slow. Very, very slow. Okay, so I'll explain it this way. Say I have I'm talking about the condition now. Say I have an object and I want to move it to the right at a very fast rate. Say I want to move it at 120 km per hour. What should I do? I should apply a lot of force. What if I don't want it to be at 120, say at 140? Then I have to increase my force even further. What if I don't want 140, I just want say 40 or 60? I should reduce my force. What if I don't want 40 or what if I don't want 60 but 20? I have to reduce my force. What if I don't want 20, I just want it to be 10? Some force is enough, very little force is enough. What if I just want to move it slowly, not even 10, say 1 meter per second, 1 kilometer per second, 1 kilometer per hour, my bad, 1 kilometer per hour. Then a tiny bit. What if I just want to move it at 1 centimeter per hour? 1 centimeter per hour. So my force is almost negligible. It's there. It has to be there. By the way, we are taking a frictionless surface. So there's no friction between the object and the surface. Frictionless scenario. So for very, very slow scenario, I just need a very, very small force, right? This has to be very, very small force for achieving that speed. What if, to this setup, I had a force which was already pulling it to the right, and this is fixed. This is 143 joules. What should I do so that I move to the right, but my speed is infinitesimally slow? So how much force should I apply on to the right? Remember, the net force over here has to be not net. Yeah, the net force has to be very, very small. So what should be my force to the right? 143.00001. Is this okay? Right? Of course, we can further make it smaller, the difference to be smaller in this manner. Do you guys agree? Can I tell the force to the left and the right? They are almost same. Force to the left is almost same as force to the right. Of course, their magnitude is same, not the direction. Right? So again, the point of this section is that I want you guys to understand the words quasi-static movement. Quasi-static movement is an object is moving, but it looks to be very, very slow. What is the condition? The condition is that the net force has to be very, very small force. And so if you have any force to counter that, we need to have an equal, almost equal and opposite force. Right? So this is important for us to understand for this particular derivation. Okay, so the derivation starts in this way. Our agenda is to move an object of mass m from point A to point B and figure out the work to do that. So we are assuming, or the setup is that the mass m is the source of the field. The test mass m is moved quasi-statically, that is infinitesimally slow, from point A to point A at a distance of Ri to point B at a distance of Rf by an external agent. So this is our background. Now, for such a moment, what kind of movement are we talking about? Quasi-static. The external agent must apply a balancing force. So F external should be equal to F gravitational pull. Right? So which is the force which is pulling towards the center? Gravity. So we have to do and work against the gravity. The same setup as this. So this is gravity for us. This is force because of gravity. And this is the force because of external agent. So they have to be equal but opposite in nature. Equal in magnitude but opposite in nature. And so we have this setup. So basically what we are looking at is, it is equal to G m by r square. So it's a function of radius. So okay, now we are have to talk about the work. So first thing is we look at the elementary work. That is elementary is elemental actually. Elemental work is a very small work basically. Elemental work. Let's see what is the elemental work by the external agent during dr. So we have the external agent has moved the object by distance of dr. So this would be ext or dr. So if I substitute this expression, I end up with g m by r square dr. Now, the next thing that we have to look at is the total work. Total external work from Ri to Rf. So what we have to do, we need to add them up. What is the best way to add? Yes, integrate. Integrate all the work throughout the journey from Ri to Rf. And so we have Ri to Rf. And this is G m by r square dr. So this is G m 1 by r square integration is minus 1 by r. And we have Ri to Rf. And so this is basically G m 1 minus r f plus 1 my ri. So a bit of rearrangement and you will end up with minus G m 1 by rf minus 1 by ri. Now this is the work done. So next we will talk about the potential difference between AB, which is given by work done by AB divided by the mass. That is work done in moving a unit object from point A to point B. That is the potential difference between A and B. That's a very definition. So basically the same expression as above, just that we are removing the chotu m. It's getting cancelled. And we have this as our this as our final expression. Okay, so okay, anyways, as a definition, this is it. And as an idea, as a mathematical expression, these are all the things that we need to do. So again, I repeat, potential difference, it can be anything. It need not be just this. It can be us pulling a rubber band. So if I pull a rubber band to certain distance, it will have certain amount of work. If I pull it to more, further away, it will have more energy stored in it. So difference in these two situations is your potential difference. As simple as that. So anything that can be compared, most of the time we can take the difference between them. So one more word, and the condition associated with it is something that we need to learn. Quasi-static. Quasi means very, very small. Quasi, that's why the word static. Static means stationary. Quasi means almost stationary. And the condition is that the net force should be almost nearing to each other. Sorry, automatically. Net force has to be almost 0. That is the force. There should be equal and opposite force. Almost equal and opposite force. So with that understanding, we can just look at this. It's a very simple scenario. We're moving an object from A to B, which is within the space of the gravitational field produced by mass m. So first we wrote the expression for force, and then we moved on to talk about the elemental work, the small work done by that force, our external force, that is. And then to figure out the total external work, we integrate it. And of course, potential difference between A and B is the work done per unit mass. And so we got this expression. That's it.